Now we'll see that crystal field splitting actually influences many factors. It influences the electronic configuration, it influences the magnetic character, it influences the color of the compounds. These were the things which could not be explained by the valence bond theory, but crystal field theory just tried to explain all those concepts with the accuracy. So just look at the board that how it influenced the electronic configuration. So before we do that, you should know that what is actually crystal field splitting, as you all know, but still we'll recall that. What happens when the ligand, suppose this is my metal atom and this is my ligand. So when ligand approach this metal atom, the metal having the d orbitals, earlier they are degenerate orbitals, now their energy just gets split, right. So there is a chance that the energy of T2G is greater and energy of EG is smaller, or there can be a chance in which the energy of EG is more and energy of T2EG is less. Right, so there can be anything. Now if we talk about the octahedral complex, so we know that in octahedral the shape is something like that, right. Here the ligand can enter from this place, this place, this place. So that means there can be 6 entries actually, right. So there can be so many entries, it can enter from this place, this place, this place, it can enter from any axis. So as we have seen that mostly when it enters from x square minus y square side and dz square side. So that means these are going to it is going to enter through the axis. So when it is going to enter through the axis, we know that the orbitals of these ones are on the axis. So they will suffer more repulsion, and as a result their energy will be higher. So we can say that their energy just gets higher, that means EG ones, and their energy is somewhat lower, right. And you know that energy difference is given by delta with O as subscript, which indicates the energy difference for octahedral complex. So there is a splitting of energy in this way. Now if we talk about tetrahedral, for tetrahedral shapes, you know that the energy for this T2G, that is dxy, dyz, dzx is more depending upon the side from where the ligand enters as compared to the energy of dx square minus y square and dz square. That means Eg possess less energy and T2G possess higher energy, right. So there in tetrahedral the energy of T2G is more and Eg is less, and in octahedral it is indicated by delta with subscript T, the energy difference, and here it is delta O indicating that their energy is somewhat higher and their energy is lower, right. So this is going to be same every time, but now depending upon that which ligand actually enters, you know that the splitting can be more or splitting can be less. That means there can be a strong difference of energy or there can be a weak difference of energy. Likewise, it can happen in this case. There is a chance that they have more energy gap or there is a chance they may have less energy gap. And it merely depends upon the ligand, that whether it is strong field ligand or it is weak field ligand. We know that the strong field ligand can create a lot of energy difference, that means it will create a long energy gap, and as far weak ligand will create a short energy gap, means a small energy gap. Like if I take an example of CO, so CO is going to create a lot of energy difference whether it is octahedral or it is tetrahedral, and if I talk about iodine, it is going to create a less gap whether it is octahedral or it is tetrahedral. Right. So now we are going to start with the electronic configuration, that how the electronic configuration gets changed. Suppose if I say that the gap between the orbitals, whether it is this or this, it happens in the same way. Suppose I have this kind of complex, I am talking about this tetrahedral one. As you know that in this case T2G is having higher energy and EG is having less energy. So if I say that if I have an orbital like this, and you can also do it for an octahedral, let me make that also, because so that you should not get confused. So this is my T2G and this is my EG with high energy. So now suppose if I have 3 electrons, then I am going to fill in this way. according to Hund's rule of maximum multiplicity. Now if in case I have 4 electrons, then what I am going to do is whether I am going to fill in this or whether I am going to pair them up, right. Only these two things we can do actually. Either we can pair them up or we can just add an electron to this side. So now what factor decides that the electron pairing will take place or electron will enter to this different energy orbital? So it is the actually that whether the ligand is strong field or whether the ligand is weak field, it is going to decide that. If the energy difference is small, that means we have weak field ligand, then obviously the 4th electron is going to enter here. But if it is a strong field ligand and there is lot of energy difference, then what is going to happen? It is not going to enter here, it is going to pair up here. So according to that factor means it decides that whether the electron is going to enter into this orbital or it is going to paired up. This is the thing we decide. And you know that if the pairing occurs, then it is called as, it will possess less number of unpaired electron and it is going to be called as low spin complex, right. So whenever, keep in mind, whenever there is a strong field ligand, it is going to cause pairing, and due to pairing there will be less number of unpaired electron, that is why it is going to be low spin complex. But if in case we have the weak field ligand, then that means the electron is not going to enter here, there will be small energy difference, so the electron will going to get excited into the another level. And as this complex, you can see there are a lot of unpaired electrons as compared to the before one, so that is why it will form high spin complex. Right. So this is how it describes the electronic configuration. Same thing will happen in this case. If the energy difference is, if there is a strong field ligand, energy difference will be more, then the pairing will occur. And if the energy difference, it is a weak field ligand, there is less energy difference, then the electron will enter into that orbital. So this is how it is going to form low spin and high spin complex. So I think it's clear that how the electronic configuration is actually changed when depending upon that which ligand is approaching. It is just a matter of that it is a strong field ligand or a weak field ligand. According to that, the splitting will occur, according to that the energy difference will occur, and according to that the pairing or the electron will enter into the another orbital. Second is the magnetic character, that how it explains the magnetic character. This we have already done. Now how it explains the magnetic character. Suppose in this case, if I am forming this high spin complex, you can see there are a lot of unpaired electrons. Lot of unpaired electrons means it corresponds to the paramagnetic character. But if I was talking about the strong field one, so strong field ones have a lot of energy difference. So in that case, the electron doesn't enter here. If it is D4, it gets paired up. Right. So that means it will possess less number of you can say unpaired electrons, so that means it is going to be diamagnetic. So if all the electrons get paired up, it is diamagnetic. If it possesses the unpaired electrons, it is a paramagnetic. So just depending upon the energy difference, depending upon the ligand which is approaching, depending upon the ligand how much energy gap it is creating, whether the excitation is possible or not. So just depending upon that we decides the magnetic and the magnetic character as well as the low spin or the high spin complex. Now coming to the color, that like we know that it is an identification property of the compounds actually, that most of the transition elements form colored compounds, right. So that means coordination compounds are mostly colored. Now what is the factor that make them color actually? So we are going to just look at this, that how the color of the substance is decided. So just look at the board. So what happens actually, suppose it is a strong field ligand, so there will be a lot of energy difference. But if it is a weak field ligand, there will be a small energy difference. Small energy difference means the light of smaller wave, shorter wavelength can excite even the electron. So that means if I have an electron here, suppose I say I have the electron here and there is a small energy difference, so that means the light of visible region can actually excite an electron. So that means the electron will remain in this high energy state for certain period, and after some time it is going to just return to its original level, and when it returns to its ground level, it will just radiate or emit the energy it has been absorbed, and that energy also falls in a visible region. That is why the color of the compounds are or you can say they are colored actually. So I think it's clear that how we determine the color. So if somebody is going to ask you about the color, you are going to say that if the energy difference is less, so we can have the excitation. See, stronger is the ligand, less is the energy, higher wavelength is required. We have the formula like this, because as we know E is equal to hc over lambda, so we can say E is inversely proportional to wavelength. So that means stronger is the ligand, right, less is the energy and higher is the wavelength required to excite it. So that means if weak is the ligand, there will be more energy and the less wavelength of light can be used, and that wavelength corresponds to the visible region. That visible region can actually cause the excitation, and the electron, when this thing jumps to an excited state, it remains there for a certain period of time, and then finally when it returns back, it emits the energy absorbed by it, and it falls under the region of the visible region. That means 400 to 700 nanometer. That is why the compounds are mostly colored, right. So this is how you are going to explain how the excitation occur. So depending upon the excitation, it corresponds to the color of the substance. And you know that the color which is emitted is always a complementary. Color which is emitted is always a complementary. This you have to keep in mind, because it's not like that it is, if it is absorbing certain amount of radiations, it is going to emit those. No, the color is obviously going to be complementary of the radiation which it has absorbed by it.